A spheroid, or ellipsoid of revolution, is a quadric surface obtained by rotating an ellipse about one of its principal axes, in other words, an ellipsoid with two equal semi-diameters. If the ellipse is rotated about its major axis, the result is a prolate spheroid, like an American football or rugby ball. If the ellipse is rotated about its minor axis, the result is an oblate spheroid, like a lentil. If the generating ellipse is a circle, the result is a sphere. A spheroid has circular symmetry, because of the combined effects of gravity and rotation. The Earth's shape is not quite a sphere but instead is slightly flattened in the direction of its axis. For that reason, in cartography the Earth is often approximated by an oblate spheroid instead of a sphere. The current World Geodetic System model uses a spheroid whose radius is 6,378.137 km at the equator and 6,356.752 km at the poles. The word spheroid originally meant an approximately spherical body, admitting irregularities even beyond the bi- or triaxial ellipsoidal shape, and that is how it is used in some older papers on geodesy. Equation. The equation of a triaxial ellipsoid centered at the origin with semi-axes A, B and C aligned along the coordinate axes is the equation of a spheroid with Z as the symmetry axis is given by setting A equals B. The semi-axis A is the equatorial radius of the spheroid, and C is the distance from center to pole along the symmetry axis. There are two possible cases: C less than A, oblate spheroid; C greater than A, prolate spheroid. The case of A equals C reduces to a sphere. Properties. Area. An oblate spheroid with C less than A has surface area. The oblate spheroid is generated by rotation about the z-axis of an ellipse with semi-major axis A and semi-minor axis C. Therefore E may be identified as the eccentricity. A derivation of this result may be found at a prolate spheroid with C greater than A has surface area. The prolate spheroid is generated by rotation about the z-axis of an ellipse with semi-major axis C and semi-minor axis A. Therefore E may again be identified as the eccentricity. A derivation of this result may be found at. These formulas are identical in the sense that the formula for can be used to calculate the surface area of a prolate spheroid and vice versa. However, E then becomes imaginary and can no longer directly be identified with the eccentricity. Both of these results may be cast into many other forms using standard mathematical identities and relations between parameters of the ellipse. Volume. The volume inside a spheroid is: if A equals 2A as the equatorial diameter, and C equals 2C as the polar diameter, the volume is curvature. If a spheroid is parameterized as where is the reduced or parametric latitude, is the longitude, and an, then its Gaussian curvature is and its mean curvature is. Both of these curvatures are always positive, so that every point on a spheroid is elliptic. Aspect ratio. The aspect ratio of an oblate spheroid, ellipse, B, A, is the ratio of the polar to equatorial lengths, while the flattening F is the ratio of the equatorial polar length difference to the equatorial length. These are just two of several different parameters used to define an ellipse and its solid body counterparts. Applications. The most common shapes for the density distribution of protons and neutrons in an atomic nucleus are spherical, prolate and oblate spheroidal, where the polar axis is assumed to be the spin axis. Deformed nuclear shapes occur as a result of the competition between electromagnetic repulsion between protons, surface tension and quantum shell effects. Oblate spheroids. The oblate spheroid is the approximate shape of many planets and celestial bodies, including Saturn, Jupiter and the quickly spinning star, Altair. In particular, cartographic and geodetic systems for the Earth are based on a reference ellipsoid. An extreme example of an oblate planet in science fiction is Mesclun, in Hal Clement's novel Mission of Gravity. Prolate spheroid. The prolate spheroid is the shape of the ball in several sports, such as in rugby football. Several moons of the solar system approximate prolate spheroids in shape, though they are actually triaxial ellipsoids. Examples are Mimas, Enceladus, and Tethys and Miranda. In contrast to being distorted into oblate spheroids via rapid rotation, celestial objects distort slightly into prolate spheroids via tidal forces when they orbit a massive body in a close orbit. The most extreme example is Jupiter's moon Io, which becomes slightly more or less prolate in its orbit due to a slight eccentricity, causing spectacular volcanism. It should be noted that the major axis of the prolate spheroid does not run through the satellite's poles in this case, but through the 2 points on its equator directly facing toward and away from the primary. A famous example in science fiction is Jinx in Larry Niven's known space. It is also used to describe the shape of some nebulae such as the Crab Nebula. The atomic nuclei of the actinide elements are shaped like prolate spheroids. Many submarines have a shape which can be described as prolate spheroid.